Hello and welcome to the Autodidact Scientist Algorithm series. I'm going to be giving you an intuitive insight into a variety of algorithms that are used in machine learning. I'm your host, Rich Gregson, and before we get started, I would greatly appreciate it if you would like this video and subscribe to our channel. So, what are we going to cover today? The algorithm that we're going to cover today is polynomial regression. Polynomial regression fits a non-linear relationship between the value of x and the corresponding conditional mean of y. So what is polynomial regression? Now, like linear and multilinear regression, it's a supervised machine learning algorithm, and it models the relationship between a dependent variable, usually denoted as y, and an independent variable, usually denoted as x. And it builds this relationship as an nth degree polynomial. And there are three common types of polynomial used in machine learning: linear, quadratic, and cubic. And it's also known as a special case of multilinear regression in machine learning, because we add some polynomial terms into the multilinear regression equation to convert it into a polynomial regression. So if you take a look at the equation of polynomial regression at the bottom of the current slide, you can see that the x variable differs in degree when compared to simple linear or multilinear. Now, x with the power of n, these powers convert the polynomial shape into a parabola. So polynomial regression models are usually fit with the method of least squares. And the least square method minimizes the variance of the coefficients under the Gauss-Markov theorem. So why do we need polynomial regression? Now, polynomial regression is able to model non-linear separable data, and it's much more flexible than linear regression. And as we've seen from the previous slide, the equation, it's x that is squared or cubed. It's not the beta coefficient. So technically, this means that polynomial regression still qualifies as a linear model, and this makes it a nice, easy, and straightforward way to model curves without having to invoke a much more complex non-linear model. And further to this, there are a large range of different functions we can use for fitting polynomial regressions. We've got sine, radical basis functions, wavelets, and splines, for example. But saying that, there are some disadvantages to using polynomial regressions. We need good knowledge of our data in order to select the best exponents. And if we don't select the best exponents, the model will be prone to overfitting. And what that ultimately leads to is that the model may not be able to generalize very well outside of the data that we've trained the model on. However, we can prevent underfitting and we can prevent overfitting as well by two processes. One is called forward selection and the other is called backward selection. Forward selection increases the degree until it's significant enough to define the best possible model, while backward selection is the reverse. It decreases the degree until it can define the best possible model. Now, there's also quite a strong disadvantage to polynomial regression, and that is it's very sensitive to outliers, to a point where one significant outlier can drastically skew the results of the model. Okay, so what are the assumptions for polynomial regression? The first one is that the behavior of a dependent variable is explained by a linear or curvilinear additive relationship between the dependent variable and a set of k independent variables. The second one is that the relationship between the dependent variable and any independent variable is linear or curvilinear. The third one is that the independent variables do not depend on each other, i.e. they're not correlated. And the fourth assumption is that the errors are independent, normally distributed with a mean zero and constant variance. So as you can see, there isn't much change in the assumptions of a polynomial regression when it's compared to a linear or multi-linear regression. So how can we use polynomial regression on real life data? What are the use cases of polynomial regression in real life? How's it being used? I've listed 3 that we use polynomial regression for. The first one, death rate prediction. So the number of people who are going to be hurt or killed during disasters like pandemics, fires, tsunamis, and earthquakes and whatnot must be predicted by crisis management teams. And they need that prediction so they can allocate resources effectively. Crisis management teams always need to be ready for these sort of events. So, because it can take days or even months to lessen the effects of these particular catastrophes. So by examining numerous independent variables, polynomial regression will allow us to create an adaptable machine learning model that will be able to report the probable death rate based on the severity of the particular catastrophe. For example, in the context of COVID-19, the variables that we would include would be things like the patient's history of chronic illnesses, how frequently they're exposed to large crowds of people, and how effective are they at accessing protective gear? What's the availability rather of the protective gear around them? The second one is speed regulation. So according to many studies across the globe, preventative measures are more successful in reducing accidents on the roadways rather than punishing the drivers or those involved after the incident has already happened. So modern speed regulation software systems, which are powered by machine learning, increasingly focus to prevent risky behavior. And by using polynomial regression in the predictive modeling, we might be able to look at trends in driving behavior such as speed, and we can warn drivers about the need to follow the law, or warn them before they even go over the posted speed limit. Another example of polynomial regression used in real life is tissue growth prediction. So different situations call for the application of tissue growth prediction. The first one is oncology patients. So tumor growth. Polynomial regression is frequently employed to monitor the growth of tumors because it takes it into account the non-linear nature of tumor growth and spread. However, we can also use the tissue growth prediction to monitor genetic growth, and this would be applied to for medical professionals to keep an eye on an organism's growth in the womb of an animal or a human. And the benefit is polynomial regression will allow us to monitor this growth from a very early stage. So we've seen a couple of use cases for polynomial regression, but how do we evaluate a polynomial regression model? Now, the metrics that we use to evaluate polynomial regression aren't too dissimilar from those used for linear and multilinear. However, as you can see on screen, I've listed R squared, mean squared error, adjusted R squared, and root mean squared error. But if you notice, I've also listed an extra one called gradient descent. And gradient descent, it's a very powerful evaluation metric. It's used throughout machine learning models, especially associated with neural networks. And what it's used for is to calculate the cost and loss function of a particular model. Now, I'm going to give a very brief overview of gradient descent, as we're going to create a number of other videos about gradient descent and in context of various machine learning models. It is a very, very fascinating subject, and it will take a very in-depth and complex look of exactly how it functions. So for the time being, as I say, brief overview, and don't worry if you don't follow along. There's going to be plenty more opportunity to for you to grasp the understanding of what gradient descent is. So let's talk a bit about the cost function and loss function. Now, the the cost function is a function that evaluates a machine learning model's performance for a given set of data. And it's a single real number that calculates the difference between the anticipated and the expected values. A lot of people do get it confused, the cost function with the loss function. So the cost function is the average of the n sample error in the data, whereas the loss function is the error for an individual data point. So to put it another way is that the loss function refers to a single training example, whereas the cost function refers to the entire training data set. So where does that come into the gradient descent? So what the gradient descent is, it's an iterative first order optimization algorithm, and it's used to find a local minimum or maximum of a given function. Now, gradient descent doesn't work for every function. There are two functions that are specifically required by gradient descent. The first one, it has to be differentiable, and the second one, it has to be convex. Don't worry if you don't know what that means. We'll get into it, as I say, in other videos. Just bear with me for now. So we've got if you take a look at the picture and the equation on screen at the moment, and the values of slope m and the slope intercept b, they will be set to 0 at the start of a function, and the learning rate, which is known as alpha, will be introduced. The learning rate alpha is usually set to an extremely low number, usually between 0.01 and 0.0001. The learning rate is a tuning parameter in an optimization algorithm that basically sets the step size at each iteration as it moves towards the cost function's minimum. The partial derivative is then determined in terms of m for the cost function equation, as well as the derivatives in regards to b. So with the aid of this equation on screen, m and b are updated once the derivatives are determined. And as you can see, m and b's derivatives are derived in this equation. So the gradient indicates the steepest climb of the loss function, but the steepest fall is the inverse of the gradient, which is why gradient is subtracted from the weights, which are m and b. The process of updating the values of m and b continues until the cost function achieves or approaches the ideal value of 0, and the current values of m and b will be the best fit lime's optimal value. So it'll be the best fit on our data sets in a polynomial form. Now I know that was quite heavy for an introduction video into polynomial regression. As I say, if you don't understand any of it, don't worry. We're going to make some fantastic videos and explain every single step of gradient events. So keep your eyes out for them videos. But ultimately, this concludes our overview polynomial regression video. So thank you very much for watching. If you have any questions, comments, or feedback regarding any of the content that you've seen, please reach out to me personally through Twitter, or reach out to the Autodidact Science channels, which we can see we've got a Twitter and a Facebook. And please support us by liking and sharing and subscribing to our channel. Thank you very much.